So you guys can see my screen? Seungyong, can you see my screen? Okay.
Yes.
Should we start or we wait a little bit?
I think we start now.
Okay. Couple of people. Okay. Good evening, everyone. My name is Wang from Tencent AI Lab in China. This is AsiaGraphics Web Seminar Section 4. Today we have two speakers. We have two very interesting talks about image restoration, image deblurring. So the first speaker is Seungyong from POSTECH, Korea. Seungyong is a professor of computer science and engineering at POSTECH. He received a PhD degree in computer science from KAIST, and then he did postdoc in New York, and later he visited. During his sabbatical years, he worked at MPI Informatics and also Creative Technologies Lab at Adobe. That's where I used to work. So we knew each other for a long time, and we collaborated on many interesting projects. So he's probably the most famous work is image deblurring and the photo upright adjustment. So today he's gonna talk about image defocus deblurring. So let's see what he's going to talk about. Okay, now it's your turn, Seungyong.
Okay, yeah, thank you for the introduction.
So I'm gonna stop sharing.
Yeah, let me share my screen. Okay. Okay. No, I'm not sure what happens. You are. Can you see my screen, right? You can.
Yeah, I can see you, but if you
okay.
Oh, now it's good.
Okay.
Go ahead.
Yeah, thank you, and thank you for the introduction, and thank you for the organizer of this AG webinar for inviting me. And today I will talk about this topic, single image defocus deblurring. Let me see. Okay. Yeah, defocus blur happens when we take a picture and when we have some shallow depth of field. Shallow depth of field means that some part of an image has focus, but some other parts are blurry. Yeah, in this example, you can see this part is very sharp, and some other parts are blurry. Here, like this, we have some little blur, and this part is very blurry. I think you can even see this part, right? Then, okay. Let me move this. Joy, can you see from my screen, or you see this part as well?
Oh yeah, I see your yeah.
Slide and also this
attendees.
Yeah,
you
right.
can
I think
minimize it.
Yeah, I stopped sharing, and I will share my PowerPoint instead of screen. Let me try again. Yeah, suddenly my computer is getting very slow.
You might want to just minimize that window.
I cannot do that. I don't know why.
Oh, because now I see a black area in that region.
Oh, black area.
Yeah, it looks like it's yeah. The part of the slides are still kind of blocked.
Okay.
So
And I
because of
stopped.
that window.
I think this is about the streaming. Then
That's okay. Take your time.
yeah. Let me try again. Try to show right. What about this? Now it's okay? Same problem?
It says we can't it's coming. Yeah, it's the same problem. We still see like a black region. So
I share.
so you yeah, even you share only PowerPoint, but if it's like occluded, that's still occluded. It seems like you have to minimize that window.
Okay.
So
How can I minimize the window?
Because I can minimize it. No, we're waiting. Yeah, it's the same thing.
Okay.
That's interesting.
Then
another thing we can do is we can switch the order of the talks. If so, you can have some time to maybe figure out how to adjust it.
yeah, usually I don't have any problem, but today suddenly I have some problem. Okay. Yeah, let me reboot my slide and then try again, and
Okay.
if it still doesn't work. Then I share the screen. I only show the PowerPoint. And then now you can see my PowerPoint only, right?
Waiting.
No.
Yes, we can see your PowerPoint, but yeah, it's still the same thing. It's the right side of your slides are blocked, occluded.
Yeah, okay, then yeah, I guess Jinshan can go first, and then I will reboot the computer in the meantime.
Okay, so can you stop sharing?
Sure. Sorry.
That's okay.
I go out and then come back.
Okay. All right. All right. Sorry about the technical issues. So let's switch the order of the talks. So the next speaker is Jinshan Pan. He's from School of Computer Science and Engineering, Nanjing University of Science and Technology in China. Jinshan is actually also an old friend of mine. So we have worked together a long time ago. Right now he's a professor of the School of Computer Science and Engineering, Nanjing University of Science and Technology. He received his PhD in computational mathematics from Dalian University of Technology, and also a joint training PhD in UC Merced. So his research interests include low-level computer vision, image video restoration, enhancement, and related problems. He's area chair of CVPR 2022. Today, he's going to talk about deep image video restoration networks. So Jinshan, I'm gonna hand it over to you right now.
Okay. Let me first
Let me-
share my screen.
Can I, oh, did I? Okay, now you can share your screen.
Okay.
Okay, go ahead. We can see your screen.
Can you see my screen?
Yeah, perfect. Go ahead.
Okay. Let me adjust my screen. Is this okay?
Yeah, I think so.
Okay. Thanks for the Dr. Wang's introduction, and also thanks Professor Lee's invitation. It is a great honor to share our work here. And in this talk, I will introduce our work about how to explore the knowledge of image degradation to constrain the deep neural networks for better image restoration. The classical image restoration problems include the image deblurring, image dehazing, image superresolution, image dehazing, and so on. So the goals of these problems are to restore the clear images from the gateway input. And we know that these problems can be usually formulated by this image degradation model. YB denotes the degraded image, and I denotes the latent clear image. F denotes the degradation mapping function, and N denotes the image noise. For example, if we take the image deblurring as an example and assume that the blur is uniform, the degradation process can be formulated by this linear convolution model, where the blurred image is usually modeled as the convolution of a sharp image with a blur kernel and plus noise. And here we use the star, denotes the convolution operator. For image deblurring, I think Professor Lee will give more details about the blur, especially for the defocus blur. And he also has done lots of great works in image deblurring. And many our deblurring works are mainly motivated by his researches. So for image deblurring, and we know that it is quite challenging because we only know the single blurred image and don't know the sharp image, blur kernel, and noise. So similarly, in image dehazing, we can use this linear model to describe the haze process. And this problem is also ill-posed as we only know this haze image and don't know the clear image, transmission map, and atmospheric light. So generally speaking, the image restoration problem is ill-posed, which usually contains many possible solutions. For example, in blind image deblurring, we can find many solutions that satisfy the blur model. And therefore, the task of blind image deblurring is to find this group of solutions. So to solve this problem, most conventional methods usually take a probabilistic approach. And here we take image deblurring as an example. The probabilistic approach usually models the posterior distributions of a latent clear image and blur kernel given the blurred image. And this term can be decomposed into the likelihood term priors on the latent image and blur kernel. So based on this approach, we need to model the properties of the latent clear image, degradation factors in the degradation mapping function F. For example, the blur kernels in blind image deblurring and the image noise. So most conventional image deblurring methods mainly focus on designing effective image priors to solve image deblurring. And during the past several decades, they have made significant great efforts to design effective image priors to solve image restoration problems. And this slide is from Michael Elliott, which gives the evolutions of the image priors. And I think we are familiar with this evolution of the image priors. For example, the energy-based ones and the widely used total variations, sparse coding, and so on. And we also have witnessed that the key success of the conventional methods mainly stems from designing kinds of effective image priors. So with the defined image priors, we can use it to better constrain the solution space to obtain high quality clear images. We know that the prior-based approach is able to generate physically sound results because it is based on a clear physics model. And in addition, this approach usually have a good generalization ability compared to some data-driven approaches. But these methods also have some limitations. The hand-crafted priors are based on the statistical observations, which may not model the inherent properties of the clear image, and thus lead to unsatisfactory results. For example, in this case of image deblurring, if the priors for the latent clear images are not defined well, and we can't effectively restore a clear image with the fine details. Another problem is that as the priors are designed more and more complex, the corresponding optimization problems becomes more complicated, which are difficult to solve. And this significantly limits the real applications of these prior-based methods, for example, on smartphones. And in recent years, deep learning has been applied to image restoration and provides an effective way to solve this problem. It plays a dominant role in recent restoration tasks. These methods greatly simplify the problem of formulation, where we only need to prepare the training data and design networks to directly estimate the clear images from the degraded image. So compared with the prior-based approach, we don't need to model the properties of the degradation factors, latent clear images, and so on. And we have also witnessed significant progress in image restoration due to the use of kind of deep neural networks. And here are listed the evolutions of the deep neural networks for image super resolution and based on this survey paper. And we can see that the network designs become more and more complicated. And some key components in these networks, for example, the channel attention, are borrowed from high-level tasks, which do not consider the degradation process. And in addition, based on the conclusions of this survey paper, the networks contains more and more network parameters. So like this figure, which may lead to the limited generalization ability. And to summarize, the deep learning-based methods have some merits as mentioned before. For example, they greatly simplify the problem formulation because we don't need to design prior on the degradation factors, latent clear images, and so on. In addition, due to the better representation ability of deep learning, the deep learning-based methods usually have better representation ability on modeling the properties of the clear images, and thus generating high-quality clear images. However, based on the aforementioned survey paper, the limitations of the deep learning-based methods are also obvious. And the first one is that the designed networks are more complicated blind black boxes. And we should know that this is a generic limitation of the deep learning-based methods, which is not limited to the image restoration tasks. Due to this limitation, the performance gains are mainly due to the use of large capacity models in some restoration tasks. And in addition, if the networks contain more parameters, it will increase the difficulty of the training process. And the trained deep models are likely to overfit in image restoration. For example, when we use deep learning to solve image restoration, the networks trained on the dataset 1 may not generalize well on the dataset 2 for the same task. And in addition, the generalization ability on the real-world application is not good compared to the handcrafted prior-based methods. As in this case, for blind image deblurring, the deep learning-based methods do not always perform better than the handcrafted prior-based methods. So since both the prior-based approach and the deep learning-based ones have advantages and limitations, it is of great interest to keep their advantages and avoid their limitations. And our motivation is that whether can we explore the knowledge of the image restoration to guide the deep neural networks instead of simply increasing the network parameters to overcome the limitations of most deep learning-based methods for better image restoration. So based on this motivation, I will introduce how to explore the physics model and the domain knowledge to better constrain the deep neural networks for image and video restoration. So now let me first introduce our work on how to explore the physics models to constrain the deep neural networks for image restoration. I will start from the GAN models. Since the GAN has been proposed, it is widely applied to many varying tasks. In image restoration, it is applied to image super resolution, image dehazing, image deblurring, image dehazing, and so on. And we also note that these methods share the similar network designs, but achieve amazing results compared to the prior-based methods. So a question is that, does the GAN-based methods really solve the image restoration problems well? So the answer is no. If we carefully analyze the GAN-based methods for image restoration, for example, in image dehazing, although it is able to remove haze from this haze input, but it also introduces artifacts. And we also found that these artifacts usually lead to the results that do not satisfy the degradation model well. However, for the prior-based approach, they do not introduce the artifacts. One main reason is that they require the generated clear image satisfy the degradation process during the optimization process. However, they do not effectively remove the haze because the hand-cooperated prior may not model the inherent properties of the clear images well. So one question is that, can we explore the properties of the prior-based approach to constrain the GAN-based methods to overcome its limitations for image restoration? So based on this motivation, we developed a PhysicsGAN framework where it introduced the constraint from the degradation process. And here is the model of our PhysicsGAN framework. The first part is the commonly used GAN model for image restoration. The second part, it denotes the constraint from the degradation process. And this equation also demonstrates that we do not only require the generated image satisfy the degradation model, but also require that the regenerated image has the similar distributions to the degraded input. And here is the overview of our methods on uniform image deblurring problem. During the training, the proposed methods include the forward stage and the backward stage. The forward stage is the conventional GAN model that is widely used for image restoration. And the backward stage is used to impose the generated results, for example, G or B, to satisfy the degradation model. And when the proposed model is trained, we can use the forward stage to directly estimate the clear image, for example, G or B, from the degraded input. And thus, the backward stage is only used to constrain the network training. As our method is based on the supervised learning approach, we apply the same degradation factors, for example, the block kernels that are used to synthesize the training data in the backward stage. Next, I will show some results to demonstrate the effectiveness of the proposed methods. And here is the applications on the real captured text image deblurring. And we know that the GAN-based methods is based on the feed-forward model to estimate the clear images from the blurry ones. And we can see that it does not effectively remove the blur from this blurry image. And in contrast to the GAN-based methods, our proposed method involves a backward stage that uses the physics model to constrain the network training, which thus obtains much clearer image, and the characters are much more clearer. So for image deblurring and related restoration tasks, one may ask whether the contents of the generated image are reliable or not. Because we all know that the GAN-based methods usually generate fake contents. To answer this question, we use the OCR accuracy as the evaluation matrix. And we can see that the GAN-based methods generate the results with the lower OCR accuracy values than the SIN-based methods. And this further demonstrates that the GAN-based methods introduce the fake contents during the restoration process. And in contrast, the OCR accuracy is improved significantly by exploring the physics model in the GAN framework. And here is the application on face image deblurring. Other methods usually fail to generate reliable results. And in contrast, our methods still obtains much clearer face image. We further demonstrate the effectiveness of our methods on image deblurring and compare it with the GAN-based methods. And we can see that exploring the physics model in the GAN framework is able to remove rain. And here is the application on image dehazing. And we know that the pix-to-pix method is based on the conditional GAN model. And we can see that it generates the results with significant artifacts and color distortions. And in contrast, our method is able to remove such artifacts and obtains much clearer image. The above-mentioned methods explore the physics model in the intensity space, and we know that most deep neural networks perform in feature space. Therefore, we further extend this work into deep feature space and develop a feature dehazing unit based on the Haze model. So for image dehazing, and we can use this physics model to describe the Haze process as mentioned before. And based on this physics model, we can estimate the clear image by this equation. If we apply a deep feature extractor F to this equation, and we can get this model in the deep feature space. And here F denotes the deep feature extractor. And with further some mathematical derivations, we can finally get this model. So based on this model, we develop a feature dehazing unit to estimate these two components and use these two components to estimate the clear features Fi, so that we can use the clear features to better help the clear image reconstruction. And finally, we embedded the feature dehazing unit into a deep convolutional neural network with an encoder and decoder network architecture to solve the image dehazing problem. And we also demonstrated the effectiveness of the proposed feature dehazing unit. And we can see that using the proposed feature dehazing unit is able to help image dehazing. Next, I will introduce how to explore the domain knowledge of videos to constrain the deep neural networks for video restoration. So for video deblurring, the blurred frames are the integration of the clear frames along the trajectories during the explore time. And this physics model is first proposed by Dr. Cho, Professor Lee, and Dr. Wang and from their SIGGRAPH work. And we can see that this is an ill-posed problem because we only know the blurry video and don't know the trajectories H and the clear videos I. So to solve this problem, conventional methods usually explore kinds of image priors to restore clear videos. As mentioned before, these methods also have a better generalization ability, but the image priors usually lead to complex optimization problems, which are difficult to solve. The other main critical problem is that these methods are usually sensitive to the motion blur estimation. If the restored intermediate latent video contains small errors, they will significantly affect the following motion blur estimation. So to solve this problem, most existing deep learning-based methods usually develop end-to-end trainable networks to solve this problem. And we also know that these methods also achieve state-of-the-art performance on kinds of benchmark datasets. However, as mentioned before, most of them, the performance gains of the most deep learning-based methods are mainly due to the use of large capacity models. In addition, although decent performance has been achieved on the synthetic datasets, they do not perform well on the real-world applications. And in machine learning, we know that although using more parameters will reduce the training error, but the trained models are likely to overfit. And here we give an example to illustrate this problem. And this example also shows that existing deep learning-based video deep learning methods do not perform well on the real-world applications. And we can see that they do not effectively remove the blur. In addition, we further note that most existing deep learning-based methods estimate the alignment information from the blurry input. However, based on the blur process of the video, the alignment information is related to the clear frames instead of the blurry ones. And thus, these methods do not follow the degradation process well. And to overcome these problems and design a compact model for video deblurring, we estimate optical flow from the intermediate latent frames. Motivated by the alternative minimization methods that is used in conventional video deblurring approach, we develop a new cascaded inference approach to iteratively update the optical flow and the latent frames. And in addition, we also note that in a video, not all the frames are blurry. We can explore these clear regions or subpixels to help video deblurring. And one effective method is the temporal sharpness per hour, which is first proposed by Dr. Cho, Professor Lee, and Dr. Wang. For example, we can use more adjacent frames to choose the subpixels based on the temporal sharpness per hour. And the temporal sharpness per hour is defined based on this equation. And in addition, we can also use the patch matching methods to select the clear regions for better image restoration. And here is the overview of our framework. And we can embed the temporal sharpness per hour into an end-to-end trainable network and develop the cascaded training method to solve the video deblurring problem. We also demonstrate the effectiveness of the cascaded training. The results show that without using cascaded training, it's not able to remove the blur well. So like this figure. While using the cascaded training methods, obtains much clearer frames, but the network parameters are still the same as this baseline method. And we also know that as the proposed cascaded inference involves several stages, we further examine the effect of the number of the stages. We can see that using more stages can improve the performance. However, the improvement is not significant when using more than 2 stages. And thus, we use two stages in our methods, considering both the efficiency and the effectiveness. And here we show the effectiveness of the temporal sharpness per hour on video deblurring. And we can see that the proposed methods obtains clearer images due to the use of temporal sharpness per hour. And in addition, using the temporal sharpness per hour does not increase the model parameters. And here are some comparisons. And we can see that our methods is able to generate a much clearer image with the fine detailed structures, and other evaluated methods do not effectively remove the blur. And here are another comparisons. And we can see that our methods obtains much clearer frames with clearer structures and characters. And we also show the video deblurring results on real captured blurry videos. Our methods obtains much clearer videos than the evaluated methods. This is a video deblurring results. Okay, to summarize, we saw how to explore the physics model and domain knowledge to better constrain the deep neural networks for image and video restoration. And we can better understand the relations between the deep neural networks and the image restoration tasks and derive new network architectures for image restoration. Okay, that's all. Thank you.
Thank you, Jinshan.
Okay, thank you.
So, yeah, so I'm not sure how many people are online, but if you have questions, you can post in the chat window. I can start with one question. Can you go back to your slide 22? I think that's a
22.
That's a main equation for the physics-based model.
This one.
Yeah, I'm just trying to understand because you went a little bit fast. I just want to go back one, like 22, the equation.
This one.
Okay, so for the physics model constraint, so for deblurring, you need the blur kernel here, right?
Yes.
So basically, it can only be trained with synthetic data. Is that right?
Yes.
Okay. What is DG and DH?
Okay. The DJ is used to let me see. So the DJ is defined based on this equation. It is used to distinguish whether the generated image J or B have the clear distribution, has the clear properties or not. It is based on the standard discriminator.
Mm-hmm.
And the DH is used to distinguish whether the regenerated image, so the J or B will be replaced by F or J or B. And this one, D or I, this I will be replaced the degraded input.
Mm-hmm. Okay. Okay. Yeah, it's a it's a little bit. It takes a little bit time to digest this equation. But what? But this okay, it's conventional GAN plus. So how do you determine the alpha here? It's just a fixed parameter, the weight.
Yes, the alpha is determined empirically based on the experimental results. So we don't have any theoretical results on this value. It is just based on the experimental results. So I also found that when people ask how to about the block kernel in the test stage, so in the information.
I'm sorry. So there is a question.
I just saw one question in our
right.
Zoom
so
information
from YouTube for the PhysicsGAN model on image deblurring. What if we do not have the blur kernel at test time?
Oh, okay. Maybe I will introduce the framework of our methods, because in the training stage we use the blur kernels, but at the test stage we only use the feed forward models and don't use the feedback stage during the test stage, because the feedback stage only used to constrain the network training. After the network is trained, we do not need the blur kernels in the test stage. I think, yeah.
That's true. Yeah, I agree. So I guess another question I have is, so here for image deblurring, you have a physics-based model, but actually for video deblurring, you can still derive a physics-based model, right? Because video, we know how video, the blurring video is caused by camera move, by camera shake. So, but in the second work, you use a kind of domain knowledge-based approach. Is that because the physics model is kind of a little bit too hard to describe or something like that?
Yes, because the physics model, we just motivated from the degradation process and don't use the physics model in the video deblurring problems, because it is hard to solve this problem in the deep learning based methods. And for the domain knowledge, we use the temporal sharpness prior, which is proposed by your SIGGRAPH work.
Right.
So the physics model mainly motivated our method like this one, because we found that based on the degradation process, the alignment information should be related to the clear frames instead of the blurry ones. But most existing deep learning based methods usually estimate the alignment information, for example, the optical flow information or the offset based on the deformal convolution. And these offset are all estimated from the blurry input. And I think these approaches will not generate physically sound results.
Okay. Yeah. All right. So if there's no more questions, let's thank Dr. Pan and switch to Dr. Lee. Seungyong, are you ready?
Yeah, let me try to share my screen again.
Okay.
Okay, I will stop.
Jinshan, you can stop sharing now.
Thank you. Thank you.
Thank you. Seungyong, you can try sharing your screen now.
Yeah. What about this? Now it's okay?
Oh, perfect. You go
Okay.
ahead.
Finally, it's
Finally.
perfect.
Yeah.
Yes. Yeah. Okay, let me begin. Yeah, right away. Yeah, today I will talk about this single image defocus deblurring. And the defocus happens by the shallow depth of field. That means some part of this image is very sharp, this part. Some other parts are blurry. Yeah, this defocus blur is caused by some circle of confusion. That means that this is some simplified camera model. And we have some focal plane. Focal plane means that the object at the focal plane will be very sharp on the image sensor, image plane. But some other object up from this focal plane will be blurry, because you can see that one point on this defocus plane will be mapped onto some circle, not a single point. Then we have some blur. Then also from this diagram, you can see that the defocus blur depends on the depth from the camera sensor. Okay. Then also the defocus blur is caused by the circle confusion. That means that the blur shapes are similar among different pixels, even though the blur size depends on the depth and can spatially vary. The defocus deblurring means that we want to restore all in focus image from a defocus image. Here, yeah, obviously this is better than this one. Then also this defocus deblurring can help some image recognition task. For example, here you can see this segmentation is much better when the input has been defocus deblurred. But there has not been a lot of research on this defocus deblurring using deep learning. And also we can compare this defocus deblurring with the motion deblurring. I mean, already Jinshan mentioned this deblurring problem. Here, this is a typical example of motion blur. Motion blur means the image is blurry because the camera was shaken through this trajectory. But in this example, the corner is like a trajectory. That means we have some 1D integration of pixel value in this blurred image. But in contrast, in the case of this defocus blur, we have this, I'm not sure you can see my mouse, probably not.
Yes, we can see it.
Okay, great. Yes. Then here, the defocus blur corner is like a disc shape. That means more pixels are merged to produce this defocus blur. That means this defocus blur is probably more similarly reinforced than motion deblurring. Then also there is no big data set for defocus deblur, and then it's not easy to apply deep learning to this task. Yeah, traditionally, we used this two-step approach. That means in the first step, we estimate the defocus map. That means we assume some typical shape of defocus blur, such as disc or Gaussian blur. And then defocus map estimation can give us the size of a blur at each pixel. And then we apply some non-blind convolution to obtain the final focus image. But in this case, usually the defocus map estimation is not perfect, and also this simple assumption of disc or Gaussian shape of defocus blur is not very accurate, and the result was not perfect. Recently, end-to-end deep learning method has been proposed for defocus deblurring. The technique was based on this DPD. The technique is DPDNet, and it was based on a data set that contains some dual pixel defocus deblurring images. That means here, as you can see here, we have some two images, like dual pixel stereo defocus image, like left and right defocus image. And then they also have some ground truth. Then their network, this kind of network, is trained to produce this orient focus image from this merged defocus image. That means they produce one single defocus image from this stereo defocus image, and then the network is trained to produce this one from this one. But in this paper, they simply use some standard UNet structure, and the network didn't fully exploit the property of defocus blur, and then the performance has some rooms for improvement. And recently, I worked on this defocus Deblurring problem, and today I will introduce two of my recent papers on the topic. The first one is about the iterative filtered network for defocus Deblurring. Then here, we simply try to design some speculative network for defocus Deblurring. Then our key idea is to estimate some adaptive filter. Adaptive filter means here we have some input image and we have some feature encoder. Then we want to deblur these features basically. But instead of directly estimating defocus features from this encoded feature, instead we predict some filters needed for defocus deblur. Okay, then, and this IFAN is our model to predict this adaptive filters, and this will be our filter, and then we apply this filter to these encoded features, and then we produce some defocused features, and then eventually the defocus feature will be used for decoding to produce this final output. But that is the main process. Then our main idea lies at this iterative filtered network to produce this adaptive filter FD blur. And this FD blur is basically consists of some stacked separable Deblurring filter. Then this filter should be spatially varying, because at the beginning I mentioned that the defocus blur will change depending on pixels. Even though their shapes are similar, their size or scale will vary depending on the depth from the camera at each pixel, right? Then our predicted filter should be spatially varying. And then to handle this spatially varying filter, we use this iterative adaptive convolution. This iterative adaptive convolution consists of separate filter, and also we apply the separate filter iteratively. Then basically, by having this separate filter, we can handle some larger receptive field. That means when we want to have some larger receptive field, we have to have some larger corner. But having a larger corner means we need some more memory, right? Then here, by having some separate filter, we can reduce the memory requirement and still can handle the larger receptive field. Then also, when we use some separate filter, we may have some error, because separate filter maybe could be less accurate than the ordinary filter. Then to resolve those possible error, we apply this filter iteratively. Then we can handle the error caused by this separate filter. Then basically, yeah, that was the idea. The idea was that here we encode a feature and we apply this. We have this IFAN model to predict this iterative separable filter. And then we also some other component in the network training. One is the dissipated map estimator. Yeah, at the beginning, I mentioned that the defocus blur size depend on the depth or distance from the camera. Then also we know that the depth from the camera is related to disparity in the case of stereo image, right? But in the in our data set contain dual pixel images. That means we have left and right stereo images, right? Then we use the stereo image for this training of our network. Then here in our network, we have some disparity map estimation module, and here we estimate the disparity, which is related to depth, and also that disparity also related to defocus blur size. Then by having this disparity map estimation, we can have more accurate prediction of this deblurring filter. But this dual pixel image needed only for training. Generally, in our test phase, we do not have dual pixel images. Then, but in this in our setting, this dual pixel image is only needed for training, and in the test phase, we do not need this dual pixel images. Then here we can see some example of displacement estimation. Accurate displacement estimation means accurate estimation of defocus blur size. Then also to further increase the performance of our network, we also have some deblurring network. This is it. Then here we predict the filter kernel for deblurring, but from that kernel we also try to estimate the reblur kernel. That means here this is the reblur kernel. Then when we apply this reblur kernel to the input, we get the ground truth sharp image, we get the blurry image. Then the reason for this reblurring is that if we can successfully reblur this sharp image to the original input, that means this deblur filter contains some enough information about the blur shape and size, right? Then this deblurring network can help to train our IFAN model to predict more accurate this deblur filter. And in summary, we have this network structure, and by having this displacement estimator and deblurring network part, we can obtain better performance of our network. In the training page, we use this DPDD training set that contains some dual pixel captured by Canon EOS camera. And this data set contains some pairs of defocus image and all-in focus image. Then we can have some supervised training. The object function contains these three terms. Then here, IB is a defocus input, and I mentioned that this data set contains the dual pixel stereo image, and then this is the output. This reblur loss means with the reconstruction loss, our network should produce a defocus result similar to ground truth. And this is about the displacement estimation. Then our displacement estimation should produce some proper disparity. Proper means that when we apply the disparity to the left image, the left image should go to the right image, or the other way around here. And also reblurring error means that when we apply this reblurring filter to the ground truth sharp image, we should get the original input deblurred image. By having these three objective functions, we can train our network nicely. And this is the result. First we show some aberration study result. So when we have this displacement estimator, we have some improvement in the accuracy. Then this part is about the iterative filter prediction, and then this part is a reblurring network. Then you can see by adding this component one by one, we can obtain some increased performance of our Deblurring network. This is a comparison with previous work. You can see that our network achieved the best performance. Then interestingly, this DPDNet D is using dual pixel, which means stereo pixel image for defocus, deblurring. But our network use only single. We do not, in our network, we do not use those stereo input, but even in that case, our network can show better performance than this one using dual pixels. Then also you can see here, in terms of computation cost, our network has a smaller number of parameters and runs faster. This shows some like a qualitative comparison. Here you can see this is the best result, best previous result, and then ours is better. Then also here you can see ours is better than the previous one. Okay. And to test the generalizability of our network, we built some real defocus blur test set. Here, this is a test set because we only capture 50 pairs. I mean, taking this real defocus blur data set is not easy. Then we simply take small number of examples. Then we use it for only testing, not for training. Here we have this dual camera system like this. We have some beam splitter, and the input light is splitted into two parts, and we have two cameras, and one is captured ground truth, and the other is capturing some defocus blurred image. Then this is another pictures. And then here we have some like a test set. When we use those test set for previous method and ours, we can see that ours works best in terms of like PSI analysis, and some other measures. And this shows some qualitative comparison again. This is the input, and this is result of previous work, and then ours is much better than previous one. That was the first paper. Then in the paper, in summary, we proposed some network architecture, and then we proposed some training scheme, and also we built some real data set for testing. Yeah, that was kind of good, but still we have some concern, or we are not quite very happy about the previous result, because we realized that even though the network works very good for defocus deblurring, still the network does not fully exploit the inherent property of defocus deblur. You remember at the beginning, I mentioned that in the case of defocus blur, the blur shape is similar, but even though the blur scale can change depending on image pixel position, right? But in the previous paper, we only use spatially varying property only, but not specifically some specific inherent property of defocus deblur. Then in this paper, we try to exploit this specific property of defocus deblurring based on inverse corner. Okay, then simply we found this property. Inverse corner has some similar property to the original defocus blur corner. I will explain the property in more detail shortly. Yeah, let me first briefly explain what the inverse corner is. This is a typical blur equation. This is blurry image, and then this is corner, and this is sharp image, and this is noise, right? And here you see it, then we usually use convolution for displaying this Deblurring model. Then when we apply this Fourier transform to both sides, we get this one, ignoring this noise part. And then here we want to obtain this x, and by manipulating this equation a little bit, and then we get this one here. We move this one here, and then we apply inverse Fourier transform. We get this one, and then we can take out this part, and eventually we get this one, right? That means in terms of Fourier transform and inverse Fourier transform, we can obtain the final, our desirable sharp image by using this inverse corner. Using means here by convolving this inverse corner to the input image, right? And this is the inverse corner. Then here you see that this inverse corner can be obtained by applying some Fourier transform and inverse Fourier transform. And as you just saw, yeah, deblurring or deconvolution can be handled by applying inverse corner. But when we try to use it, we found that you will see that usually the inverse corner size, inverse corner is much larger than the Blur corner. Then also the convolution with inverse corner is very sensitive to outlier. Then here you see that some artifact when we obtain this Deblurring result by inverse corner. But still, when we use CNN, like convolution neural network, this concept of using inverse corner for defocus blur or deblurring may work quite well. Then we try to use this concept of inverse corner in our in this paper. There are some key ideas. The first one is that when the scale of defocus blur changes, here again, you remember I mentioned that in the case of defocus blur, the shape remain almost same, but the scale is changing. When the scale of defocus blur changes, the shape of the corresponding inverse corner remains the same, but only the scale changes. That means here we have this corner for defocus blur, and then we upsample. That means same corner but with different scale, and then we take the inverse, and we obtain the inverse corner, then we get this one. But this is the same as this one. This one is obtained by, we have this corner, and we obtain the inverse corner, and we upscale. Then this is the same, okay? Then also we can verify that using some example here. This is the result obtained from this one, and this was from this one. You can see that they're almost same. But what does that mean? That means that in this defocus blur image, we have small defocus blur here, middle, and large, right? Then we can apply inverse corner to remove defocus blur from this part. Then, in that case, the inverse corner needed for deblurring this part and this part and this part will have the same shape, single shape. Then only the scale may change, right? That is the meaning of the first key idea. Again, to deblur these different pixels, we can use the same inverse corner, but only the scale of the inverse corner need to be changed. The second key idea is about how to represent all the different scale of inverse corner. Yeah, it may be hard or impossible to represent all the different continuous scale of inverse corner. Then we simply use some discrete set of inverse corner. Then we do some interpolation. Yeah, in this example, to handle the focus blur of this image, we need this kind of scale of this inverse corner. But we approximate this scale by interpolating this small scale and large scale. And here, this example shows that this is a result of applying this inverse corner to this one, and we obtain this one. Then by applying this inverse corner to here, then we obtain this one. Then by interpolating these two images, we can obtain the result of applying this inverse corner to this one. Okay, then that means that when we apply this inverse corner to defocus, deblur this image, we apply some discrete, some large, middle, and small scale of inverse corner to this one. And then we can interpolate the result of this convolution. Then here, for example, this part is a large defocus blur, and then we apply this. Then let me make it clear. Then here we apply these three scales of inverse corner, and we obtain three images. Then we interpolate using some weights. Then for this part, the result of this inverse corner will have a larger weight because it has a larger blur. Then here, this part has a middle scale blur, and then the result of this middle scale inverse corner will have a larger weight, and this part is handled by this smaller scale inverse corner, something like that. Then here, this means that we deblur this input by using different scale of inverse corner, and then we interpolate using some weight depending on the defocus blur size. The last idea is that we have to represent this different scales of inverse corner, but it's not very immediate. It's not very straightforward. But we found that if we use this dilated corner, then this dilated corner will have the same component in the corner, and then it's easy to share the same weight for this in this dilated corner. That means by having this dilated corner with the same weight but different scale, we can represent same inverse corner but with different scale very easily. Okay, then here this example show that this is a sampled inverse corner with a larger scale, and that this is like a spatially sampled inverse corner with the same this larger scale. But when we apply these two, this one and this one to this input, we obtain very similar deblur result. That means this dilated corner is enough to deblur this given input blurry image. Then we design this network using these three key ideas. Yeah, basically we approximate this equation. You remember this equation here. We approximate this equation using some network. Then we first, but we do that in the picture space. That means we have some encoding and decoding part, and we process this encoded picture using these layers. Then this layer is a convolution layer approximating inverse corner, but they have the same weight. They share the same dilated corner but with different scale. And then we have some spatial scale attention model. Then here we have some interpolation of alpha value. Then this scale attention determine this interpolation factor for these different scales of inverse corner. Then by having the scale attention, we can handle different scales at each pixel. And also we have some channel attention. Here we call shape attention. That means this inverse corner has multiple channels, and then by having some channel attention, we can handle slightly different corner shape among the different pixels. Then this is our final network structure. And then for training the network, we use the same data set used for previous paper. Then object function is very easy, like reconstruction loss and perceptual loss. And then this result, then first we can show that by sharing the weight means that we assume the inverse corner is the same shape. Then we share the weight among different scales of dilated corner. And then by sharing this weight, we can obtain some better accuracy. And also here we have some component like a directed convolution unit for inverse corner and the scalar shape attention. Then this number show that each component has some help, has some roles in improving the accuracy. Okay, and then here you see that I mentioned that scale rotation is determined the weight for interpolating different corner scale. Then, for example, here, this part has a very large defocus blur. That means the dilation rate 5 has some higher weight. And we can have the clear Deblurring result here. This is a comparison with some other previous work. Then here you can see our network produced the best result. Then more importantly, our network is very simple. Here you can see that our network is very fast and it has very small number of parameters compared to previous work. Because our network is designed by fully exploiting the specific features of the focused blur. There's some other result. Then here you see that by comparing this result, and you can see that our result is better than previous ones. Yeah, another result, and ours better. Okay. Yeah, today I introduced some two novel single image defocus blurring method. The first one is based on this iterative filter adaptive network. And the second one is based on corner sharing parallel atlas convolution. And here, both of them can produce orient focus image, as you can see here. When we compare these two techniques, the first one has some more capability, right? The network structure is more complicated than the second one, as you can see here. Then it has more capability. Then we also introduce some training strategy, such as a dissipate map estimation and Deblurring module. And it works well. It's powerful. But the limitation of this technique is that the network is too big, kind of like complicated. In contrast, the second approach is based on fully exploiting the nature of inverse corner for defocus blur. And then the network is very simple. Then the training is easier, the inference is simple. Then even though it's not as powerful as the first one, it can handle mostly common shapes of defocus blur. And then there are some pros and cons, but generally this is more compact and probably more useful in practice. Even though we proposed two new techniques for defocus blur, we still have some limitation. Here, yeah, this part is kind of like a saturation, the overexposed part. And also here we have some different shapes of defocus blur. And then in those cases, like some irregular shape of or strong highlight may have some difficulty to our technique for defocus blur. Then probably in the near future, we can generate some data set containing various types of defocus blur, and then we probably or hopefully we will be able to handle more general kinds of defocus blur. Okay, that was it. Yeah, thank you, and I hope there are some questions.
Yeah, thank you,
I'll be happy
Seungyong.
to answer. Yes.
Yeah, very nice work. Very interesting.
Thank you.
I think one thing I'm impressed most about your work is that you always kind of pay attention to the computational cost of the method. So
sure.
So you always, yeah, so many of your work that the resulting models are small, compact, and runs pretty fast. I think that's pretty important for real world application.
Yeah, you know that I'm mostly interested in real application of my technique.
Yes, that's good. And also, as the first work, actually, in the concept, it's very similar to Jinshan's idea of physics-based models, because you also have a blur model, like a blur process, like a in the training process, use that linear blur model to. So yeah, it's
this part, yes.
Yeah, conceptually it's very similar to
Right.
Jinshan's work. So I guess if I mean good methods, I mean people are often find that if something really works, then people will find it in different ways. Yeah, that's good. So I do have a question here. So about the training data, you used dual pixel images, right?
Yes.
I guess to me, dual pixel images are kind of like stereo pairs with a very small baseline.
Yes, exactly.
So I was wondering if someone don't have a dual pixel camera, can they kind of use a regular stereo pair, like a camera setup, to capture images and train the network? Is that gonna work?
Oh, okay. Yeah, I think it's very good idea actually, because when we have some stereo images, we can estimate the disparity, and then we can estimate little depths, right? We can estimate depth, and then we can estimate the size of the defocus blur. Right. And then that can be a good good data set for training this kind of defocus blur. Yeah, I think it's possible. Yes.
Yeah. So, but although you use dual pixel pairs, but your method in testing time, it only takes one image.
Yes. Yes.
So if you were to, I mean, if you mentioned that some other methods take two images as input.
Yeah,
right?
this one here. Yeah, this one. So this one was done by the authors proposed this data set. Then they have two versions. This one is using only one. I mean, without dual pixel, and this one is using dual pixel. Then in their method, the dual pixel based method works better. Like here, you see that. Yeah. But our technique is not using dual pixel, but even in the case, ours is better than their dual pixel method.
Right. That's good. Do you think your method can be modified to take both images?
Oh, sure. Oh, I think we. Yeah, I don't remember about this paper, but we tried it. We did that for the second paper, and then for the second paper, it worked better. Yeah, the performance got improved actually. Yes.
Right. So so also I saw that in the last slide about the limitations. I think we worked together on handling kind of highlights many years ago. Right? Remember we had a paper, but it looks like we still have this problem. Do you think it's because we don't have a model in the kind of deep learning approach to explicitly handle the outlier, the highlight?
I think so. Highlights? I think so. Yeah, I mean, as you know, deep learning is basically try to learn the mapping from the input to the output, right? But the highlight is only a small part of the training data, right? Right. And then probably, I guess, but this is my guess, our trained deep neural network, and in both cases of this defocus deep neural and motion deep neural, probably our trained deep network is trying to ignore the defocus blur part, because it's better for the network to try to handle better the majority part of the blur, which is not highlight, right? And I think we should some specific mechanism or some specific component that employs the deep network to explicitly handle those highlights. And without that, it will be very hard to handle this highlight.
Okay, that makes sense. We do have a question from YouTube. The question is it possible to create and use synthetic training data sets while lens simulation,
Yeah.
path tracing with physics-based lens models.
Yeah. Yes. Today I didn't mention my previous paper, but I worked on the defocus map estimation, actually. I mean, at the beginning, I mentioned I mentioned the traditional approach use this two-step approach, right? The first one is estimate this defocus map, and then we deblur, right? Then I worked on this defocus map estimation. Then to do for the defocus map estimation, we use some training set, synthetic data set produced by actually graphics rendering using this lens model, actually. The name is the SINDOP data set, something like that. Yeah, you can find the paper and data set on my web page. Then for the defocus estimation, we use this thin lens model and produce some synthetic data set that we train the network. But of course, in that case, we have to handle some domain gap between this synthetic data and real images, right? Then I think we can do something similar here. That means we generate some synthetic defocus blur data set, and then we handle domain gap. But we didn't do that because, as I already mentioned, now we have some real data set for this defocus deblur. This is a real data set. But still, the size of this defocus blur data set is small, kind of, and then we may augment this data set using some synthetic data. Yeah, I think that should be possible.
Yeah. Okay. Okay. I don't see any other questions. So let's conclude this session. First, I want to apologize for the technical difficulties we had earlier in the beginning. We didn't have a very smooth start, but I think the talks definitely worth it. With that, I'd like to thank Professor Seungyong Lee, Professor Jinshan Pan for their time and their very insightful talks. And we will see you guys next time. I think this concludes our session. Thank you.
Yeah, thank you. Thank you.
Thank you.
Yeah,
Bye.
bye.
I hope to
Bye.
see you soon.
Yeah, see you soon. Bye.
Bye.